Thank you very much. Yes, hi everybody. My name is Bjarke Gotfredsen, and I have an accent. So let's keep it with that. Yes, my background is software development, and I developed these small components that you are using because I wanted to get into electronics, and I wanted to make it as easy as possible. I wasn't interested in sitting and soldering and using oscilloscope and multimeter and things like that. I want to click something together and get quickly to a point where I could start working with it. So that's of course you know, both good and bad. You know, maybe I don't learn enough about electronics. On the other hand, I get more productive, and I think that's what a lot of the stuff we use today is about, is kind of like get result faster. In the old days, when I started going to school, it was a long time ago, we have to do calculation on a piece of paper, and that was very good. But you know, it wasn't very fast, and eventually we have calculators, and now I'm not sure I know how to do a division on a piece of paper. You know, I'm gonna grab a calculator somewhere. And that's how we develop. We kind of like have stuff that we use that is becoming more and more accessible for everyone. So I want to just go through a little presentation I have. It's just 5-6 slides about the bus we're using on our chips. And let me just share my screen like that. And then I have to run the presentation. And then, are you all seeing a Perfect. Screen that says I2C twice? Okay.
Yes.
So thanks. Good stuff. So the presentation is about I2C specifically. But before I get into that, then let me talk about this term buses. And there's nothing to do with the picture there, where you see a number of different buses. In electronics, we talk about a bus where you can send signal from multiple devices over kind of like the same, we call it infrastructure, to other devices. So here are some buses like USB. So you can plug multiple different USB devices into a computer. And if you can't plug into a computer, you can plug it into what's called a hub, which is kind of like a little, you know, similar to when you have an extension cord for your power. You kind of like need more plugs for your power. Then you have like a little power bar, and you can plug in the different things, and then you extend it to the plug point. USB works kind of the same way, and same kind of, there's a reason why it's not exactly like that. Ethernet, so that's your network. Now most of us use Wi-Fi, but back when we have to plug something into a computer, like a cable, that was an Ethernet cable, and that's also like a bus. That was like you plugged into the wall, but at the end of the wall, that's set like a switch, which took all the different internet connections and distributed them to servers or other computers in the building. Then we have a bus that's a little special, and that's the serial bus. So that is something we also have on our device. But the problem with serial bus is that you can only connect two things. You have something in one end, and you have something in the other end. And if you want more on a serial bus, then you have to start implementing other kind of protocols. In the old days, it was called UART. In the US, was also called RS-232, and it's kind of like the oldest. It was way before USB, even before Ethernet, and not, certainly before any of the other protocols. So serial and UART is a protocol that stretches back to probably the 1960s or 50s or something like that. But all these protocols, or these buses I'm talking about here, they're typically being used between like bigger computers. And then a number of years ago, one kind of like somebody figured out that, hey, if we have like some electronics, how can we talk to that electronic on the same board using the same philosophy. So before we did this thing here with buses, we had like a wire from one chip to another chip for each bit they want to communicate. So in the old days, we had 8-bit computers or 8-bit CPUs. So it'll be 8 wires going from like the memory chip to the CPU chip. And in, I think back in the 90s, 80s, late 80s, starting 90s, we started getting, first 16-bit and 32-bit, and now we have 64-bit. So that means that if you have a memory chip and a CPU chip on your motherboard, then you have to have 64 wires going across. So wasn't there something we could do that's a little bit smarter? Maybe not for everything, but for example, if we just need like to figure out what is the temperature on this motherboard, then we need a temperature chip, but we don't need to read it that fast. I mean, the temperature doesn't change that fast. And then we came up to, what about this I2C? So I2C stands for inter-communication, inter-circuit communication, something like that. So, so the idea is that 2 computer chips talk to each other using I2C, and it's meant to be on the same PCB, the same, like I'm holding up a PCB here, so it's meant to be the same chips on one PCB. Similar with that, probably before I2C came out, SPI, which is also, it's a serial, so this is like some serial protocol interface to also talk to the different devices. And I2C and SPI was like the 2 versions I was considering. USB, Ethernet, and serial wasn't really useful, also because a lot of those sensors, they don't talk USB, Ethernet, and serial. So you have to have something that convert from what they talk to another protocol. So you just put in a comment here, it's integrated circuits, I2C. So if I wanted to talk USB from one device to another, then I had to have a big, chip on it. They have to convert it from what the sensors talk. And interesting enough, most of the sensors talk either I2C or SPI. So if I used one of those 2 protocols, I didn't need to convert anything. So the difference between I2C and SPI is that with SPI, you have 4 wires from your computer to your device. So you have one that sends data the one way and one that sends data the other way. Like the serial also, like USB, none of those. Data on one pin the one way and data another way on another pin. But because they want to talk very fast compared to, for example, serial, they then have a 3rd pin, which is then a clock that simply, from the computer goes up and down. So it's like a drum, little like when you have to play music, you want to play to a certain, so everybody plays at the same speed. So you have a metronome or somebody in your orchestra you listen to, and that's the rhythm you follow. So that's a clock. So SPI have that, and I2C also have that, by the way. And then what SPI also have is that now, if I have a lot of different devices on my bus, which one do I want to talk to? So then I have a pin that I put high, give a signal and say, I want to talk to that weather chip. But if I have one that I have to say, I want to talk to that weather chip by signaling to that with one pin, then every time I have another sensor, I need one more pin. So if I only talk to one, well, in that case, I only need the 3 pins because I can actually just tell it I always talk to that. But if I talk to 2, I need 5 pins. Talk the one way, talk the other way, clock, and a pin for the one and a pin for the other, 5 pins. I'm talking to 3 chips, and I need 6 pins and so on. I2C is different because that only uses 2 pins. The one is the rhythm, clock, 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 like the metronome. And then in another pin, it can talk both ways. So it can't talk at the same time, you either listen or you speak. And in the I2C, you have something called a master. I'm getting into that. And then you're simply telling the device, now it's your turn to talk. what it have in order to figure out who should talk and who on a chat with is that everybody have a name. Everybody have what they call an I2C address, but it's kind of like just a ID. It's a name. They're like if you sit in a classroom and say, Peter, your turn to talk. Then Peter talks and nobody else talks. And the same is for I2C here. You simply just say, who do you want to talk to now? And then that chip talks. The chip knows its own address. And then it says, listen, if I'm being requested, then I know I'm allowed to talk. If there's two chips, two Peters in a classroom, then they both talk. The same here. So you have to make sure that they have different addresses. Okay, so I'm going a little bit further into I2C because that is actually what we are talking about. So here you can see an MCU microcontroller unit core talking to all these different devices. So a temperature sensor, pressure sensor, accelerometer, ambient light sensor, touch sensor, battery monitor. There's a lot of different sensors it can talk to. It can also send data out. It doesn't only have to be sensors that goes in. And the two pins is called SCL, so serial clock, and the other is called SDA, serial data. So this thing here, the MCU, is the core. And I'm gonna demonstrate how that looks like just now. And then of course, all these are slaves. And yeah, I'm sorry they use this terms master and slaves, but that's just how it was defined back in the 70s when I2C was invented. It was master and slaves. And there's a lot of terminology in electronics that's not necessarily very PC today. But until somebody figures out what they have to be called instead, I'm not gonna confuse people by calling it something else. So here, I wanna give an example using the different slaves here. So the master say, what's up? And then the slave says, sorry. And then says, tell me a joke. I can only tell you temperature. And then says 23 degrees. And it shows that to the human. So now it sends message to slave 2 and tells that what is the temperature. So that's how it communicates. It's like there's a master and there's a number of different slaves. So the way we have it here, so you recognize hopefully this core here, those two pins on the top surface, that's the two pins we're using for this I2C. So the first one is SCL, and then the second one below is serial data. And maybe just so there's no confusion, the clock is only the master that can send data out of that. The slave will never send anything. So the clock is not necessarily all the time just like going up and down. There's also sometimes a signal over the clock to tell the slave what to do next. But in general, it's just a clock that goes up and down. And then through the communication between the slave and the master, they then agree on who have to talk. The master actually tells you if it expects data from you, and then you talk at that point. And once you have spoken, then master takes over and you wait to be asked again. So these different devices have addresses. So the master doesn't have an address. That's only the slaves here. So in the case of the weather chip, it's called 0x77, and that's just hexadecimal 77. And the display is 0x3c, so that's the hexadecimal name. You can also write to them in a decimal name. That's just 60. So 3c is the same as 60 decimal. But it's typical in your coding that you use a hexadecimal address here. So there's 7 bits, so you can't go from 0 to 127. That's 2 and 7, so that's 128 addresses from 0 to 127, including 0 is 128 addresses. So that's what's available. The last bit, the reason why you can't use 8-bit is because that bit dictates whether you are reading or writing while you are talking or listening. Sorry, this thing here is just to show you that you can actually connect a lot of different chips together like this thing here. So I did an experiment a long time ago where I took a Raspberry Pi and I actually connected all these different chips that we used to have, and I see if I could actually talk to all of them. And all those that's on the screen here, I could actually talk to each and individual of all these different chips here. You can see on the top, there's some that looks the same, but there's a little solder pad on them that kind of like can change the address. The chips you have doesn't have a solder pad to change the address. That's just, we never really used it, so therefore we have taken that away. But in principle, the I2C and those two pins, you can talk to a lot of different devices. And yeah, 20X chips I had there. So here you can see when I log in and do a I2C detect, that's how it comes. 29 I2C addresses pops up. So this is a way to figure out what is the different addresses out there. So all these different chips, they responded with 29 different addresses. So the way this I2C detect works, and you can also do that in Arduino, is to go and talk to each address. And if the address doesn't respond within a timeout, then, well, there's nothing there. Otherwise, they're meant to always respond. And that's the way this thing here works. So you can see it goes not that fast. So this was sped up a bit for this purpose here. So that is that for me. I don't want to delve too much further into this thing here, but I'm very happy to take some questions and figure out if there's more I can show and tell here. Judy, over to you for
Great.
moderation.
Bjarke, thank you very much. That was really great. It certainly, what it did is it underpins a lot of what we've been discussing the last 2 weeks. So we don't actually have any questions yet in the chat. What I was thinking is, Daniel, I'm not sure if you are able to engage. I'm not sure if you are actually in your classroom right now. But otherwise, is there anybody who has questions for Bjarke? And it can relate to anything actually in terms of these X chips. You know, he certainly will be able to help you out. Okay, so Bjarke, I have a question for you, and that is, you know, we saw a whole array of 20 odd chips there that you'd connected together, you know, and I was just wondering, why don't we have all of those now, and a little bit, maybe if you just want to give us a bit of a background to this version that we are working with at the moment, which is version 1.5, you know, and in terms of what did you learn? What did you learn as an engineer? What did you learn from the first version that you had that you've now applied in terms of the second version?
Yeah, so that's a very good question here. So what happened was that when we started this up back in 2016, we slowly made more and more chips, and we ended up having approximately 80 different chips. But a lot of them was kind of like overlapping. Then, for example, we had like 3 weather chips that, you know, could all tell the temperature and humidity and things like that. We had 2 IMUs, so accelerometer, gyroscope, micrometer. We had a lot of overlaps. We had like analog to digital converter chip, and we had 2 different ones of them with different kind of like screw terminals. And we also had digital input, which actually just used the same chip, but because it was like for digital, we decided it's probably easier we had like it separately. And for each of these, we did libraries, and what happened was that even though we had the libraries, we had all these chips here, nobody used them. There was the only thing that was used was those we sold in a kit form and where we provided software. So if many of you have the starter kit, there's like 6 chips or something like that in the starter kit, and the software there, which I also wrote, is a software that kind of like makes sure you can use all those chips, and that is what most schools were interested in. And if I want to code something like that and build this thing here, you're not necessarily interested in using some highly specialized chip. Some of them was also very expensive. I mean, we had like infrared array chips that were like over $100, and we had like a lot of different chips that could do a lot of different things. But hardly any of them was used. It always came down to the same few cores, the same few whatever that we had made into a kit where we had done software. So like if you had like something that could fly with a balloon, or our CubeSat kit, or whatever of the different kits, those chips was the one we sold. We had done interface chip both to the Raspberry Pi, we had done it to the BeagleBone Black, we did it to Microbit, we did it to Minoboard, we did it to a lot of other stuff. And nobody was interested in any of these different boards. So we decided here that we do the next version, that we were going to spend much more time on each of the chips to make sure they were more functional. So for example, the core I demonstrated before, and the one with the little robot on, and the other 6 buttons that sits on this thing here have a number of LEDs that have these touch buttons. We didn't have a core like that before. Before that, we had like a core that had, I think if it had, I can't even remember if it had any LEDs on it. It had no buttons or anything like that. It was just a core, because the whole idea was that if you want LEDs and things like that, then you had another chip with that. Or if you want to have a keyboard, you had another chip with that on. So here we kind of like put some of it together. For the Blue Shift mission, we have a much more advanced chip that we've done, which have like it have an SD card, it have a camera on it, it have the core on it, and these are things that have to be on this chip because we can't actually put it externally. And we have like a little bus that allows us to put a radio on it. So there's like, you can see here's the lower radio sitting on top of the core here with an antenna. And there's like CAN bus on this thing, is that it communicates with a number of other chips using CAN bus. There's extra RAM on it, there's PS RAM and things like that. So that's kind of like where we moved the development. Instead of, we used to have a core that had an SD card on it because you couldn't have an SD card that run I2C, just not possible. And we don't have other buses on our chips. So when we have like our different chips, then we have to make sure we have a chip that we have to make sure it's I2C, otherwise we can't communicate with it. So SD cards is SPI, we don't have that. So we decided to put that on like one core here. The same with the radio. The radio we used to have on a separate core, but nobody could program it because it was very complicated, because we had an I2C to SPI converter and things like that. Now we made it much easier. This thing you can program with all the standard libraries there is in Arduino. So standard radio library, standard SD card library, standard camera library, and so on, standard CAN bus library. So it's much more important for us to kind of like do something where there's more generic used libraries. We also done like the other thing that was also on a focus was that I felt that the old chips we had was quite expensive. So what we wanted to do was to kind of like see if we could get the price, lowered, allowing more schools, more students to actually have access to this thing here. And one of the requirements in order to, lower prices, anything, is to do something at scale. And we had fewer chips, we could do bigger scale of these fewer chips, instead of having specialized chips that you nearly have to order every time. One of the big hang-ups I have in the space industry is, you want to have like a power module to a satellite, costs $5,000, or solar panel costs $5,000, whatever it is. It's always $5,000, and then you have to wait, 3 months before you get it, because they actually sit there and hand assemble this thing here for you. Well, if you just bought something electronic over the counter, which the CubeSat was actually meant to be, well, then it's probably much cheaper. And that's what we wanted to do. We want to make sure that we had like high volume, easier access, and so on. So yes, I've done the software. We don't do libraries this time because now we're focusing on recommending libraries that exist out there. So we don't put it under our shoulders to make sure the libraries is there also. There's this question here from Brittany. Hi, Bjarke, do you have any pro tips for finding good code examples for the STD kits? No. So I think that the best thing is that if you want to program. So let me just share my screen here. Hang on a second. So let me just do that. Okay. And share. Oh, can I do? Okay. So you should now see my GitHub page here. So this GitHub page, you can write domino4.com. You will automatically get to here. So if you now it says GitHub up here, but if you write domino4.com here, you get on this page here. Okay, and up here I pinned a number of different repositories. The first one here is Xchips, and if you go on that, you can see the different chips that we have. And I'm busy kind of like this is under development, so I'm showing you guys it now. But here you can see the different chips that I'm kind of like working with. So if you want to program, for example, let's say the light sensor here. So we take the light sensor. Yeah, let's take the light sensor. Then you click on the light sensor here, and you can then see this is the I2C address, and this is what the chip is called, LTR390. And then there's a suggested library. So you can go to this library here, and maybe there's many examples, maybe they're not a lot. For me, one example was there, so I use this example that's here. But you can now take this LTR390 here and see if there's other stuff on GitHub, because any 390. Sorry, I have to say all. And then you can see there's Adafruit also have a library, but that's for Python, so you can't use that. Then there's another one here, so let's look at this one here. And you can see there's a lot of different libraries here. They have also just one example. So let's go back, check if there's somebody else. There's this one here, which is also C++. There's no examples here, I think. That's from Python. But you can go and find them different places. Example I actually want to show with this thing here is actually the accelerometer. I know you don't have that in your starter kits, but if I go to the accelerometer here, then I'm suggesting a library here from SparkFun. And SparkFun always do a lot more examples. So if I go to this one and look at the examples, you can see there's basic reading settings, TET detecting, lowest power, self-test, max output, and things like that. So, but the main thing is that if you want to, use any of these sensors, then you have to simply just figure out how do you get the data out, and then the rest is your own code example you have to kind of like come up with. So if I go back to, for example, now let me just take the accelerometer here we had, okay? So go to GitHub, and I say in examples here, I say basic readings. So here is the code for basic readings. So it's not long. You can see it's like here, the bottom here is commented out, so that's not interesting. So in reality, other than there's like a Excel begin up here, you have to define it, begin to see if it can find it or not. You get your acceleration here from X, Y, and Z, and this one can also show the temperature. So here's the code for that. But that just gives the data. Now it's up to you to kind of like figure out how you can use that, okay? And you can't necessarily find libraries for everything, but then you have to maybe, find some math somewhere. So for example, if I say calculate magnitude from accelerometer, okay, close enough. Then you can see here, you get like the formula for doing that. It is just Pythagoras that you have to use for this. And now you have like an accelerometer. You can use the same to say, pitch and row and yaw, how to calculate that. And then there's other calculation. So Brittany, I wouldn't necessarily say that, and I don't actually find anybody who's doing any kind of like specific examples like that. You might find, I'm just gonna stop my sharing here. You might find that some, for example, on instructables or some of the, I think there's a hacker website. I get like an email from them from time to time where people are hacking some stuff together. You'll find like a very interesting example of something where people have used like some of the functions based on our chips, but it's not exactly that one. It might be another accelerometer, and it might be another weather chip. Then you can take that code and then modify that to use our weather chip or our accelerometer. An interesting thing that I've done is that I actually taken our new core here and the radio, so the radio that sits on this core here, plus the display, and I actually connected that and uploaded some software from something called TinyGS. So I created myself a ground station that downloads data from 14 satellites. So that is an example where I find something and then, luckily it used a lot of the stuff we had here. I mean, I had to maybe do a little bit of modification and code to get it to work properly. But hey, I got it up and running, and actually I just installed a new antenna today. So my ground station is now up and running smoothly. But yeah, I think the most important is that you start subscribing to some of these websites. There's also hackster.io. I haven't been there for a while, where you might be able to find something that's interesting that people have done. And the most important, you just have to understand, is that what kind of sensor you have. You have a weather sensor that can measure that. You have an accelerometer for that. You have maybe a CO2 sensor. You maybe have, these different things. And then you kind of like figure out something you want to use with that. Daniel, you had a question here. For those of us who are working with custom sensors, can you provide some insight into what we should be looking for in terms of sensor integration? What could we be doing to test to see if our sensors are good for this initial flight launch? Yeah. So so what I have is that I have a test software that we have a guy who packs all our chips into bags and things like that. And before he packs anything, it's all getting tested. So it tests not only for the I2C address works and things like that, but also if reasonable data comes back. You can't test it and say, the temperature have to be 23.2 degrees Celsius because it might be hotter or colder. But it's not going to be minus 15 or 600 when you sit like indoor. So it's so we have that software which I can share. Again, that's under constant development. I actually just busy with software for testing the extended core, which is being distributed soon. And there's like a lot of more functionalities we have to test. I'm busy testing that also. So and then the thing is that the software that we're going to load is of course expecting the different sensors. So we're going to make sure that if it doesn't see the sensor, that it reports back and the sensor is not there. But you know, we can certainly do both things with you know, sharing our internal test software. It uses a display and it comes out and say thumbs up and down, and also it uses the LED, you know, green and red LED to tell you if the chip is all right or not. So that may be great. It's, you know, it's I can see the point, Daniel, that you maybe get more comfortable that if you think you're sitting with something and it doesn't work and my code doesn't work and things like that, you maybe feel like, it's a chip that doesn't work. If you could then test with this thing and comes back and say, no, the chip works fine, you get like a temperature of whatever Celsius, then it's like, okay, it's my code. Just in general, it's always your code for everybody, including myself. So
yeah, so I think my question is, yeah, so my question is a little bit more poignant than that as well. So I think overall, definitely that's awesome to have obviously the software test beds, but for a lot of us, right, with our students, talking from a teacher's perspective, right, we don't necessarily have those things in place, right? So what is it that students might be able to do to look for, right, besides just, oh, our code is good or our code is bad, right? More so kind of when they're testing their sensors in the context of what is actually going to happen for spaceflight. Do you have any recommendations or kind of tips and tricks as to what kind of indicators the students might be looking for, right? In terms of being able to say, oh, this is going to be a good sensor, right? So comparing, you know, this accelerometer versus this accelerometer, and both of them are capable of working with I2C, how might they go about picking one versus the other? What is it that they're looking for in the testing?
Yeah. Okay, so I don't have anything out of it. Number one is that we only have one accelerometer, so there's only one to choose between. So that makes it easy. There is, however, as a good example with the accelerometer, you can configure a lot of these chips. So there's like parameters now. The one I showed here, this example, the basic reading was that you started and then you start reading it. But actually, with most all accelerometers I've seen, you have to tell what you are, and I call it resolution, which is maybe just a term because I know how the sensor works. But you have to tell what the max acceleration is that it can be can feel. So it's typical for most accelerometers is either 2G, 4G, 8G, or 16G of force. Okay. And the reason why you want to have it low, because why don't just send to 16G if you can measure the whole thing? Well, the whole thing is that the lesser a G you set it to, the more finer details you get, because it's like you have 16 bits, so you know you have quite a big number that will tell you what is the G-force. And if you say, well, I want to have that spread over 0 to 2G, then it's much finer than if you do it from 0 to 16G. So those kind of configurations. There's also other things, and a lot of sensors have that. Is like what's called oversampling. So what it does is that it reads a sensor multiple times and then give you an average. So it's kind of like trying to make sure that it didn't do any mistake. But if it have to do that, then you can't read it as often. So let's say you can read a sensor like once a second. Typically it's like 10,000 times a second. But let's just, for the case, say you can do it once a second. And you want to have a 10 times oversampling. Then you only get a value every 10 seconds because it has to read the 10 times and average out for you. But you can configure that. And the reason why you could do it yourself in the code, but it's much better you ask the chip to do it, because if the chip does it, then you can say, well, I'm going to do something else in the meantime. I'm going to read that sensor and that sensor and that sensor, and I'm coming back to you. And in the meantime, it may be done 10,000 readings and done an average and giving an average back. All those kind of things is parameters you have to set up in the code. Not necessarily have to set them up, because there's always a default or standard that 90% of us uses. But for example, when we put a kit on the International Space Station, you know, there's it's called microgravity for a reason. I made sure that the maximum gravity that the chip was the lowest value was the 2G. And of course, it was the max it actually had when it's on space station was 0.005 G or something like that. It was not very high. But otherwise, then it's a good good thing. So you mentioned here. So I think what we have to do is kind of like come up with, and I think it's slightly related to Brittany's question about what is a good things you can run with the sensors, because especially when it comes to setting something up in space, most of us have an idea about what is the temperature here, what will be in a rocket, we don't know. What is the acceleration? What is the acceleration when it flies in a rocket? What's the acceleration when it lands and things like that? What should we set it to? So I think we have to maybe come up with something like that to do together with Blue Shift to kind of like figure out what is the interesting thing to come up with here. Okay, Judy, any other questions? Hackster is, I think it's CK. It's a CK.
Yeah, sorry.
Yeah. Well, it's close to top of the hour. So,
Bjarke, thank you very much. That's wonderful. And so, yes, what we'll be doing is we'll be posting the video. And if it's okay, if you wouldn't mind sharing your slides, I'd also like to share your slides with those who
I will send them to you.
Them. That's absolutely great. Terrific. So yeah, it doesn't look like we have any more questions. So thank you very much, everybody. And next week, we're going to be covering the science of payload. We're going to have 2 iterations of payload. So next week, we're going to be looking at our first